So in this lesson, we're going to take a look at how you calculate the derivative of the natural logarithm function. So we want to be able to find the derivative of a logarithmic function with base e, okay, including combining this with the chain rule to find the derivative of composite functions. And then, of course, eventually we're going to be able to use this derivative rule to solve the standard calculus problems that we've been working on throughout the course. So for finding the derivative of the natural log function, let's go back to the derivative rule that we learned in the last lesson. We know that if the function that we are working with is y equals e to the x, the derivative, y primed, was e to the x. So that was our derivative formula for an exponential function, base e. What we want to do in this lesson is find the derivative of a function y equals ln of x, ln being our natural logarithm. And to do this, we're going to make use of the fact that taking the natural logarithm, or the logarithm to base e of something, is the inverse operation of having an exponent to the base of e. So I can take something like y equals ln of x, and I can take both sides of this equation here, and I can raise them as exponents to the power of base e. So I can write the left-hand side as e to the y, and the right-hand side as e to the ln x. Okay? As long as I do the same thing to both sides of this equation, I still have a valid equation. Now, on the right-hand side, because we've got a base e down here, and we've got ln, or logarithm, to the base e up in the exponent, it's like these two things cancel each other out. So this is actually e to the y equals x. So really, I've just taken that logarithmic equation that we started with and rewritten it as an exponential function, or an exponential equation. Now, let's say we wanted to take this thing that we have here, e to the y equals x, and take the derivative of both sides of it. So derivative with respect to x of e to the y, derivative with respect to x of x. Now again, I still have a valid equation because I have done the exact same operation to both sides of my equation. Okay? As long as I do the same thing to both sides, everything is okay. Now, the right-hand side is pretty easy. What is the derivative of x? Well, if I'm doing the derivative with respect to x of x, that's just 1. The left-hand side is a little trickier because what we have in here is actually a composite function. Okay, we've got e to something, and then we've got y, which is itself a function of x. Y is a function of x. Okay? So when we do this derivative, we've got to use the chain rule. So our outer function is e to the something. So we know that the derivative of e to the something is just that original function. So the derivative of e to the y is going to be e to the y times, what is the derivative of that inner function? Well, our inner function is what's up in the exponent. It's that y. So the derivative of y, we're not really sure, so we're just going to write y primed. So the whole derivative of that left-hand side is e to the y times y primed. Now, what are we actually trying to find here? We're trying to find the derivative of our original function, y equals ln x. So we want to take this expression that we've got here and solve for y primed. So let's see, how can we do that? Well, what is e to the y? Right here, we found that e to the y is actually equal to x. So we're going to replace that with x. So we have x times y primed equals 1. And then if we rearrange this for y primed, we have y primed is equal to 1 over x. And that's our answer. So if y is equal to ln x, then y primed is equal to 1 over x. And that's our derivative rule for the natural logarithm. Okay? Derivative of the natural log function is 1 over x. Now, what if we have a composite function? Something like y equals ln of g to the x. And I'll put big square brackets to indicate what we're taking the ln of. So we're taking the ln of some function, g at x. Well, then we have to use the chain rule. Y primed equals, our inner function is this g to the x, so it kind of takes the place of x in this rule that we have up above. So the derivative of ln of something is going to be 1 over that something, so 1 over g at x, times the derivative of that inner function. That inner function is g at x, so the derivative of g at x is g primed at x. There we go. Derivative of the natural logarithm function, derivative of the natural log function combined with the chain rule. So let's take a look at 4 quick examples here, just to sort of hammer this thing home. So our first example, pretty simple, y equals ln of 5x. So right away we've got something that involves the chain rule. Our inner function here is that thing we are taking the ln of. G to the x is that 5x. So we know that the derivative of that inner function, g primed at x, is just going to be 5. So our derivative here, y primed, is going to be 1 over that inner function, so 1 over 5x times 5, which simplifies nicely. Those 5's cancel, and we just have 1 over x. Okay. So our next example here, we've got y equals ln of x squared plus e to the x. Our inner function is this thing that we are taking the ln of, x squared plus e to the x. So what is the derivative of that inner function going to be? See, we've got 2 functions added together, so we want to do the derivative of the first one plus the derivative of the second one. First one is just x squared, so we know the derivative of x squared is just 2x plus, second function is e to the x. We know the derivative of e to the x is just e to the x. So 2x plus e to the x is the derivative of that inner function. So let's actually do our chain rule here. So we've got, we're doing ln of x squared plus e to the x. First term in our derivative, well, if we're doing the derivative of that outer function ln, it's going to be 1 over whatever is inside those brackets. So 1 over x squared plus e to the x times the derivative of that inner function, 2x plus e to the x. And that's about as good as it gets. We can't really simplify anything there, so we could just leave it like that. All right, our next one here. Y equals ln x over x squared. All right. What do you think you should do with this one? Any thoughts? We could rearrange it so it would look like ln of x times x to the negative 2. And Lynn has already told us that we're going to use the product rule to do our derivative. So our two functions, u is ln x, v is x to the negative 2. So product rule, derivative of that first function. So what is the derivative of ln x? That's the one we just learned, Maureen. 1 over x times our second function, which is x to the negative 2, plus, we need our ln x, and then we're going to multiply it by the derivative of that second function v, which is just a power function. So we're going to bring down the negative 2 and make it x to the negative 3. Now something like this, we should definitely rearrange it a little bit. So we're going to have 1 over x times x to the negative 2 is 1 over x cubed. And then it's going to be minus 2 times that x to the negative 3 becomes something over x cubed. And then we're going to have a ln x up above like that. So in a case like this, you're probably going to want to get a common denominator and add those two fractions together. We already have a common denominator, so this is 1 minus 2 ln x all over x cubed. Okay, and our last example here. We want to find the derivative of the ln of 3x cubed plus 1 divided by x squared plus 2x plus 1 plus 7, and then we want to evaluate it at x equals 0. Okay. So first we need to find our derivative here. Now what rules, how would you approach this derivative, taking the derivative of this function? There's an easy way and there's a hard way. Okay. The hard way would be to use the chain rule, okay, to do the derivative of the ln first and get 1 over x cubed plus 1 over x squared plus 2x plus 7, and then use the quotient rule to get the derivative of that inner function. Okay? That'll work, but it's a little bit harder. It's partially because you're using the quotient rule there. The easier thing to do is, before you try to take the derivative, simplify this using the laws of logarithms. So if I'm taking the logarithm of something divided by something else, I can change this into something where I'm subtracting two separate logarithms. So we'll rewrite this as ln x cubed plus 1 minus ln x squared plus 2x plus 7. Okay? And we've been doing this all along in the course. As when we see a complicated function, we try to rewrite it in a slightly different form so it makes the derivative easier to take. So now I can take the derivative using the difference rule. I can take the derivative of this first ln, then subtract the derivative of that second ln. So my derivative is just going to be, well, derivative of ln x cubed plus 1 is going to be 1 over x cubed plus 1 times the derivative of that inner function. So the derivative of x cubed plus 1 is 3x squared. And then I'm going to subtract derivative of the second ln function, 1 over x squared plus 2x plus 7 multiplied by, again, I'm using the chain rule, so I have to multiply by the derivative of that inner function, which is going to be 2x plus 2. Now, where would I go from here? Well, I might try to combine those fractions together, getting a common denominator, but in this question, I was asked to evaluate at x equals 0. So probably what I'm going to do is just start subbing in 0 right away, because I know, and maybe I'll add a little line here that tells me at x equals 0, so I know that I'm subbing in the zeros. I know I'm going to have 1 over 0 plus 1 times 0 minus 1 over 0 plus 0 plus 7 times 0 plus 2. So the zeros make everything kind of easy here. So I'm going to have, well, this whole term is gone. That becomes 0. So I'm left with negative 2 over 7. is the value of that derivative at x equals 0.